Hello and welcome to this clip having a look at a part question on alcohols, which is quite applied, so it's more A2 in style rather than first year. So it tells you an unsaturated alcohol has 6 carbon atoms and contains 1 carbon-carbon double bond. It also wants you to think of the complete combustion of this alcohol and construct an equation for that reaction. So that means for your carbon-carbon double bond, there'll be 2 hydrogens less than if it wasn't unsaturated. So we have 1 carbon-carbon double bond. So we subtract 2 hydrogens from what we would normally put down for an alcohol which was saturated and containing 6 carbon atoms. For the equation, the CO2 is the combustion product for the carbon due to complete combustion, and obviously for the oxygens you need to take into account the fact that the alcohol has an OH group already, so there's an oxygen atom locked up inside it, and that needs to be factored in. So with a bit of playing around with the numbers, that gives you C6H11OH plus 8.5O2, giving you 6 CO2 and 6 H2O. Then it introduces compound C, which is obviously a trial. You've got three OH groups, and it's refluxed with an excess acidified potassium dichromate 6. So that means that the OH in the highlighted pink circle now is a secondary alcohol, so that'll oxidize once to form a ketone. The one on the end there, that I've now highlighted, is a primary alcohol. That will oxidize twice, once to an aldehyde and then once more after that to a carboxylic acid. And then finally you've got a tertiary alcohol at the bottom, and that won't oxidize under the conditions the question describes. So that means you've got 3 oxidations taking place, so therefore 3 O's in square brackets are required. And for every oxidation there's a production of a water molecule, but for the oxidation that goes from aldehyde to a carboxylic acid there isn't a production of a water molecule, if that makes sense, so there's actually only 2 water molecules made. Okay, so what does that give us? It gives us a ketone, like we said, a carboxylic acid, like we said, and this one is kept as is because it doesn't oxidize, like we mentioned earlier. So then it introduces compound D. This time it's a diol. Again, it's a cyclic compound. So what happens when it's refluxed with H2SO4? It means it's dehydrated. A water molecule is removed for every OH group present, and that would leave a carbon-carbon double bond in its place. So giving a quick example using cyclohexanol. Just to introduce the idea, this isn't compound D obviously, it's just bringing the idea into focus. So if we take the OH group on the left and the OH group on the right, what's going to happen is the OH group is removed and also a hydrogen atom from one of the sides. So it doesn't matter which one really, but this is going to happen at 2 separate sites on compound D. So it gives us 2 carbon-carbon double bonds that can be in different locations like that. And those are your 3 isomers, and they all are C7H10. Then it says at the bottom, a student converts compound D into a diiodoalkane. So essentially what you're doing is you're substituting the OH group for an iodine atom. This is nucleophilic substitution. So the reagent is Hi, or hydrogen iodide, but it's produced in situ by the reaction of sodium iodide or potassium iodide possibly with concentrated H2SO4. Okay, I hope this has been a useful look at this applied question. Thanks for listening as always. Until next time, see you soon.